In this video, we're going to continue learning about the derivatives. This time, having a look at their properties and a few examples. The first property we'll see is about the sum of two differentiable functions. We have f and g, differentiable at a point A, and then the sum is also differentiable at A, and the derivative of the sum is just the sum of the derivatives. Let's go ahead and try and prove this. As we've learned in our previous video, we're going to use the definition of a derivative. So, the derivative of the sum of f plus g is, if it exists, the limit when h tends to 0 of the function I want to differentiate, that is f plus g, in a plus h minus the function in a, and all this divided by h. Now, the sum of two functions evaluated in a point is just each of the functions in the point. And the same here. So now we're going to group the terms that have f together. So we would have the limit when h tends to 0 of f of a plus h minus f of a divided by h. This is what I marked in green. And then the terms that have the other function g. So plus g of a plus h minus g of a divided by h. And now, using that the limit of the sum is the sum of the limits, and that both f and g are differentiable, then each of these limits will exist. And what they'll do is they'll give us the derivatives of f in a plus the derivative of g in a. And that is exactly what we wanted to prove, that the derivative of the sum is the sum of the derivatives. Now we're going to continue with the rule for the product of two functions. We have again f and g, two differentiable functions at a, and then the derivative of the product is the derivative of f times g without the derivative plus f times the derivative of g. Let's prove this theorem. Again, we're going to be using the definition for the derivative. So, if it exists, the derivative of f times g is the limit when h tends to 0 of f times g in a plus h minus f times g in a divided by h. So now again we use the definition of the product of two functions evaluated in a point. So this is f in a plus h times g in a plus h minus f in a times g in a. And now we're going to write this a bit differently. We leave the first term as it is, and we're going to subtract, and this is very similar to what we did when we worked with sequences and the limit of the product. So we're going to subtract f in a plus h times g in h, and then add it again. Let me move this a bit. And the last term we had is f in a times g in a, and all this divided by h. So now we're going to take common factor from these first two terms. We have the limit of taking common factor f in a plus h. We get the first term gives us g in a plus h, and the second one gives us minus g in h, g in a. And now in the second term, we're going to take common factor g of a. So this gets multiplied by f in a plus h minus f in a. And to not write the divided by h in every term, we're going to separate it. So we're going to put it here and here. These are equivalent expressions. So now let's think for a minute about this limit. F in a plus h, as f is continuous, because f was differentiable and we saw in the previous video that differentiable implied continuity, then this will tend to f in a when h tends to 0. Now this second term, because g is differentiable, this term will tend to g prime in a. And then this limit, well, g of a is just g of a. And this other term, because we're taking the limit when h tends to 0 and f was a differentiable function, then this tends to f prime in a. So then we have calculated the limit, and this gives us f in a times g prime in a plus g in a times f prime in a. And this is the product rule for the derivative of two functions. So now let's think about a very particular case about the product rule, and it's when g of x is equal to some constant that's a real number. Let's see the derivative c times f. This is using the product rule. The derivative of f here times c plus the derivative of c times f. But now the derivative of c, because c is a constant, we know this is equal to 0. We saw this in our previous video. So then this whole term is 0, and the only one that survives is c times f prime in x. So this is what happens when g is a constant. And now, using this, I want you to think about this case. The derivative of f minus g. You can think of this as f plus minus g. And then think about this minus g as a constant times our function. So with all this, we're ready to get into some examples. In the first one, we're going to consider the function f of x equal x to the power n, where n is just some natural number. What we're going to do is prove that the derivative of this function is n times x to the power n minus 1. And we're going to do this with induction. Again, if you don't remember induction, I recommend you check out the Algebra 1 videos, where we explain induction and look at various examples. So we have to start with the base case, and that is when n is equal to 1. in this case our function is just f of x equal to x, and we saw in our previous video the derivative for this function, and that is 1. And we know we can write 1 in a very fancy way as 1 times x to the power 0. And this is exactly n times x to the n minus 1. So we're fine, the base case is true. Now we're gonna have our inductive hypothesis, and it's suppose the derivative of f is n times x to the n minus 1. And we start with the inductive step, and that is considering the case n plus 1. We're gonna start by defining a function g of x equal to x to the n plus 1. This is another way of writing x times x to the n. And x to the n is our original function. So then g of x is just x times f of x. Okay, so g of x is x times f of x. And we're gonna calculate g prime. We're gonna use the product rule we just proved, that is the derivative of the first element, because we have here the product of the function x times the function f. So the derivative of x times f plus x times the derivative of f. Again, we know the derivative for x. This is just 1 times f of x plus x times f prime. And here is when we use our inductive hypothesis. We said that f prime was n times x to the n minus 1. So we're gonna be using this and saying that this f prime is n x to the n minus 1. And now we can just use the definition for our function and write this as x to the n plus n times x to the n minus 1. X times x to the n minus 1 is just x to the n. And now we can just rewrite this as n plus 1 times x to the n. So with all this, we get that by induction we can conclude that if f of x was x to the n, then f prime in x is n times x to the n minus 1. Now for the second example, we're going to be using all the properties we know so far to find the derivative of a polynomial, that is, f of x is 3x to the power 4 plus 5x squared plus 2x to the power 3 plus 1. Let's calculate f prime, that is the derivative of this polynomial. We are first going to use the derivative of a sum. So this is 3x to the power 4, the derivative, plus the derivative of 5x squared, plus the derivative of 2x to the power 3, plus the derivative of 1. Now each of these numbers is a constant multiplied by x to some power. So we can use what we learned about the derivative of a constant times a function, and we know that it's just the constant times the derivative of our function. Now we can continue by using the derivative of a constant, because the derivative of 1 is equal to 0. And now we can use what we just proved about the derivative of x to the n. This is 3 times n is equal to 4 in this case, times x to the n minus 1. 4 minus 1 is 3, plus 5 times the power 2 times x to the 2 minus 1 is 1, so x to the power 1 is x, plus 2 times the power 3 times x to the 3 minus 2 minus 1, and that is 2. And plus 0 just gives us this. So we can now rewrite this as 3 times 4 is 12, plus 10x plus 6x squared. And then this is the derivative for our function, for this polynomial. Now something that you'll see very often is higher order derivatives. So that is the second derivative, for example, of a function f is written as f2 prime in x, and that is very easy, it's just the derivative of our derivative. Okay, so you have the function, you calculate the derivative, and when you differentiate that function, the result is the second derivative. And you can do this as many times as you want. So the nth derivative will be just f, and when it's more than 3, we say like this, with parentheses n. It's just the derivative of our last derivative. So in this case with n, it would be n minus 1. This is not a power, this is not f squared, it's different to f2 prime. The same with f to the power 4 is different to f with parentheses 4, this is the derivative. And this is just the power of a function. So with this, something that's very interesting is that if f of x was a constant times x to the power n, we know that f prime of x will be this constant n times a to the x times x to the n minus 1. Then the second derivative will be just the derivative of this. So we have this exponent times the constant n times a times x to the n minus 1 minus 1 is n minus 2. And so we can go on, we can calculate the third derivative, and in this case it would be n minus 2 because it's this power times all the constants we had, n minus 1, n and a, times x to the n minus 3. So when we continue like this, we get to the nth derivative of f, and that is n factorial times a, because if we pay attention, for the third derivative we have n minus 2, n minus 1 and n. Now we're going to continue with another property. We have a function that's differentiable at the point a, and that the function evaluated at that point is different to 0. Then 1 over the function is differentiable, and the derivative is minus the derivative of g, divided by g evaluated in that point squared. So let's go ahead and prove this. Before starting and writing the limits, let's have a look at this. We know that this term is well defined because we said here that g of a was different to 0. But we don't have that necessarily for g of a plus h. But there is something we can do about this. So g is differentiable. That is this hypothesis. So then we saw in a previous video that differentiability implied continuity. So then g is continuous at a. As g of a was different to 0, then because it is continuous, we know that there exists a delta greater to 0, such that if the absolute value of h is smaller to delta, then g of a plus h is different to 0. What we're saying with this is that if this point was a, and my function did something like this, we're asking ourselves what happens here. What if I took this to be h? Then g of a plus h is 0, and then this is not well defined. Well, but because g is continuous, we know that there exists a delta such that I can take just this interval and my function will never be 0. And as we're taking the limit when h tends to 0, then we are taking h small enough to fit in this interval. So then we have, because of this, that this other part is also well defined. Because g of a plus h is different to 0 if h is small enough. So now that we have all those things in order, we can continue with the limit when h tends to 0 of 1 over g times a plus h minus 1 over g times a divided by h, using the definition of 1 over g is the limit of 1 over g in a plus h minus 1 over g in a divided by h. So taking common factor, we can write this as g of a minus g of a plus h. So this multiplied by 1 and this one multiplied by 1, and now divided by h times g of a plus h times g of a. And we're going to rewrite this a bit differently. We're going to change the order of these two terms and then write this term here somewhere else. So this is the limit of minus g in a plus h plus g in a divided by h times 1 over g in a plus h times g in a. Okay, these two expressions are exactly the same. And now I can write this, and now I can rewrite this moving this minus sign outside the limit as g of a plus h minus, because minus times minus will give us plus, g of a divided by h times this other thing. And now because g was differentiable at a, then this limit exists, and it is g prime in a with this minus sign. And this will be, let's think about this limit. When h tends to 0, g of a plus h tends to g of a. So then this product tends to g of a squared. And that is the derivative of 1 over g in a. The last property we're gonna see is the derivative of a division. Now we have two functions, and we say that f divided by g is differentiable, and the derivative is the function g times the derivative of f minus the function f times the derivative of g divided by g of a squared. Let's prove this. We're gonna use all the things we learned so far. So I can write this as f times 1 over g. And here I can just use the product rule. So this would be the derivative of f times 1 over g in a plus the derivative of 1 over g times f in a. So this is just f prime over g in a plus, and the derivative of 1 over g is minus g prime in a divided by g in a squared times f in a. Now if I multiply this first term times g in a over g in a, then what I get is f prime in a times g in a minus g prime in a times f in a, and all this divided by g in a squared. And that is exactly what we were trying to calculate. Let's finish this video with a few examples. In the first one, we're gonna have the function f of x squared minus 1 divided by x squared plus 1, a rational function. And we want to find the derivative. For this, we're gonna call x squared minus 1 h of x and x squared plus 1 g of x. So what we just saw was that the derivative of f was going to be g of x times h prime on x minus h of x times g prime on x. And all this would be divided by the one in the denominator, that is g of x squared. So to find the derivative of f, we need to find these two derivatives, of h and of g. So let's first do that. The derivative of h is the derivative of x squared minus 1. Using the derivative of the sum, we get the derivative of x squared minus the derivative of 1. And this is the derivative of 1 is 0, and the derivative of x squared is 2x. we get something very similar for g. It's the derivative of x squared plus 1. So using the sum, and then at the derivative is 2x plus 0. So now we have to put these values here in our formula. We have g of x is x squared plus 1 times h prime is 2x minus h of x is x squared minus 1 times g prime is 2x, and all this divided by g of x squared, so x squared plus 1 squared. Now we can use the distributive law, and this is x squared times 2x is 2x to the power 3 plus 1 times 2x minus x squared times 2x to the power 3, and then minus and minus is plus 1 times 2x divided by x squared plus 1 squared. But now these two terms can be cancelled out, and this gives us 2x plus 2x is 4x divided by x squared plus 1 squared. So this is the derivative of our function. And now the second example is very simple, but it's also very useful. It's a very common function, so it's an example that you'll see over and over again. And that is 1f of x is 1 over x. Well, f prime in x, this is when we call x g of x. We know the derivative for 1 over g is minus g prime in x divided by g of x squared. So this is minus g prime is the derivative of x 1 divided by g of x squared, and that is x squared. So then this derivative is minus 1 over x squared. And as I said, this is a very common function, so it's one that you'll probably see very, very often.